All right, Alan. What's up? Okay, we're going to be starting a new unit today. I have some readings for later on this unit. This is going to be an extended unit. I mentioned that last week. I have some good readings for the later parts of it, but for this introductory part, I've been having trouble finding something that introduces things in the way that I like. Still going to search around. By the latest, I'll have that posted by, let's say, Wednesday, so that you still have it for this early part, but I just may not be able to find one. But anyway, there will be other readings when we get later on into the unit to help reinforce some concepts. So you'll have that option. This first part of this unit, I'm calling repeated measures. We're thinking about cases where you have, say, the same people measured multiple times, or the same businesses measured multiple times. You have multiple units of a certain kind, and you have multiple cases, observations for that each of those units. So people, schools, workers, whatever. So before we get into the meat of this unit, I want to go back to a hypothetical that we've worked with for a long time. This data set of people evaluating grade applications. Their evaluations are on 1 to 9 scales. And the scale is a little bit weird in that lower scores are better. So in this first example, we're assuming that we have 100 people, and half of them evaluate high quality grants, half of them evaluate low quality grants, and we're just seeing whether their new scores based on low quality grants match how these grants were categorized. Did the high quality grants indeed get better scores on re-review than the low quality grants? So this is a snippet of this kind of simplified data set. I've already coded the high and low quality text labels -1/2 and +1/2, so I'm skipping that step. We have discipline ID and overall impact scores. That's the 1 to 9 score. So pretty simple data set. And the way we've approached this problem, we've looked at this problem several times now throughout the course. You have text labels, you replace them with numbers. You have an overall mean, that's the gray line. And in order to find what's the relationship between quality and impact scores, you can think about anchoring a line to this central point and pivoting around to try to find a slope that minimizes the sum of the square errors. There's going to be some slope where that's best in the sense that it minimizes those sum square errors, but it makes it so that our predictions are at least wrong. And that line might be this. And if you fit a model in R, this is the kind of output that you get. So just as a refresher, if we consider that intercept up there, how is that intercept represented on this graph?
Average overall impact between the qualities of grants.
Great, so that's like conceptual interpretation. It's the average quality across high high and low quality grants, or the average overall impact across high and low quality grants. And where would I find that on the graph?
Right in the middle there where X crosses that.
Yep.
dashed line.
So this is the y-intercept dotted line. This point right here is that average overall impact score. And specifically, you could use these two numbers to find what that number is going to be. That 3.04 is going to be the average of 3.4 and 2.7. With some ranking. What about the slope for quality? Or how is that represented on this graph?
Black line, right?
What about the black line? The slope of the black line. So that tells me, as I go from low quality to high quality, by how much do I need to modify my predictions for overall impact? And if you were to use that coefficient in a sentence, how might you describe what that coefficient tells you?
The change in overall impact from low quality to high quality grants is -0.72 units.
Great. So the change in, or the degree to which you have to modify your predicted overall impact as you go from low quality to high quality is -0.72. Or another way of thinking about it is that it's the mean difference in overall impact across high and low quality grades. So this is review. We've worked with these kinds of problems a lot. This is where we're starting at a baseline. Now I'm going to modify this problem a little bit. So before, I was working with a case where every reviewer got their own grant. I had 100 reviewers. Each of them reviewed their own grants and assigned overall impact scores. Now the problem's a little bit different. So I have 50 reviewers, and each of those reviewers reviewed 2 grants, one of which is high quality and one of which is low quality. Still have the same outcome, still have high and low quality grants, but the structure of the study is a little bit different. And actually, what I'm going to do to help facilitate comparisons across where we started and where we're going to go is I'm going to take the same data set that I showed you and just change the participant IDs. So this half of the data set, quality economists, impact score, that's all going to be the same across the 2 data sets. The only thing that's different is that whereas I had the sequence of participant IDs 1 to 100, now each participant ID is associated with 2 rows instead of 1. So you might remember in the last unit when we talked about how you can structure data sets, one way to tidy up a data set is to give each participant ID or each unit multiple rows. So this is kind of what we're doing here. Our data set is long in the sense that we have 100 rows even though we only have 50 people. And each person is associated with 2 rows instead of 1. Everybody with me? So the fact that we have multiple rows, multiple observations for each participant actually presents us with a bit of a problem. You know, this is kind of different from the various kinds of problems that we've worked with so far. So we have to figure out some way to deal with these multiple rows per participant. And it also brings a technical problem that the general linear model, which is what we worked with in the first semester, it doesn't really handle very well. So can anybody remember the various assumptions that the general linear model has. Can someone name one assumption of the general linear model?
Linearity.
Linearity, great.
Normality.
Normality,
Variance.
constant variance,
Independence.
independence. Just one other exact X. The assumption that's an issue here is independence. So independence says that if I consider each of my residuals, each of my prediction errors, knowing the prediction error of one observation tells me nothing about the prediction errors of another observation. But that seems like it might be an issue here, because if the same reviewer is giving multiple scores, if I know the score of reviewer 5 for this grade on this row, that's probably going to tell me something about their score on their second grade. So you can think about reasons this might be the case. While one reviewer might have kind of harsh scores, they're unwilling to give grades high scores in general. Another reviewer might have more lenient scores. So they're more willing to say, yeah, this is a good grade, but they say that about all grades. So the fact that we've changed the structure of this problem gives us a situation where our normal rules don't seem to apply as well as apply. We have a situation where knowing the prediction error on one row will probably tell us something about the prediction error on another row. And that's a situation where the general linear model just fits. Okay. So to try to figure out how to handle this situation, I'm first going to start with the graph of this problem. So this is the graph that we started with when we were examining the case where we had 100 people instead of 50. We're going to try to figure out how to represent this information about the link between one row and another on this graph, and that might tell us something about how to approach the problem in general. So I'm going to try to figure out how to show that certain of these dots are linked together. They come from the same reviewer. And then we'll try to figure out, well, what does that say about how to approach this problem statistically? So the first thing we can do is just consider one of these pairs of points and highlight it in red. So this red means that each of these scores comes from the same reviewer. So that's the first step. And actually, I'm going to take away all the other points so that we're just dealing with this pair of observations. So right now, I'm not considering the other 49 people in the study. It's just this one person. We're going to try to figure out if we can approach this problem with this one person. So the points were jittered before. I'm just removing that jitter because it's not necessary in order to see this one case. Well, if we consider this one case, I mean, it still is the case that we have a y-intercept, and that great line represents the average for this person. So I'm kind of treating this problem like I would any other old regression problem. It's just that I'm doing this regression process just for this one reviewer. I'm not considering any of the other reviewers. I'm doing this. People following me so far? Well, that average for this one reviewer can serve as an anchor point, so I can anchor a line to the center right here and pivot around to try out different slopes. And there's probably one slope for this reviewer that's best, in the sense that it minimizes the sum of the square roots. In this case, it's kind of obvious what that line would look like because we just have 2 points. We draw a line to link those 2 points. points. That's going to be the line that minimizes some of the square errors for this one reviewer. You follow me? So these are the values for the two scores that this reviewer gave these two grades. They gave one of the grades a 6 and another grade a 3. If you had to guess, what would you say would be the point at which this black line crosses the dotted line? 4.5. And why 4.5? One of you.
Because it's right in the middle of 3 and 6.
Yeah, well, so you could draw a parallel to what happened when we were working with groups of points. That central point was the mean of means. The mean of the mean here. Well, the mean for this one participant of low quality grants is 6, because we only have 1 point. The mean for this participant of high quality grants is 3. So you just take the mean of 6 and 3, that's 4.5. That's one way to think about it. It's halfway between 6 and 3, which is another way to think about it. That would just be 4.5 the mean of those numbers. So if you had to guess, what do you think would be the slope of this black line? I heard a couple numbers. -2. Why do you say -2?
Only because I 6, 5, 3.
Well, so one way to think about this, what did the slope of the line represent when we were working with two groups of points?
I mean,
It was, sorry, say that again.
I'm not sure.
Someone want to help out? So what did the slope represent when we were working with two larger groups of points?
The difference of the group means?
It was the difference of the group means. Great. So given that information, what would you predict would be the slope of this black line where we only have 2 points? -3. So we just have 2 points, it would be the difference between those 2 points. That makes sense? So while we're working with this one participant's or reviewer's data, we can still think of like we have an intercept for this reviewer. That intercept is just the average of the 2 points. And we also have a slope for that reviewer. And that slope is the mean difference of these 2 points. That makes sense? So this box up here is what I just showed you. That's the data for that one reviewer. I can apply the same kind of procedure to each of the reviewers in my data set, each of my 50 reviewers. So here are the data for the first 10 reviewers. I'm just showing you, the 2 scores that each reviewer gave to their high and low quality grants. And here are all 50. So of course, for each of these reviewers, I can find the average score that they gave their 2 grants. That's the gray line in the center. And then I can anchor a line to that central point where the gray line meets the y-axis. And I can pivot around those lines for each reviewer until I find the slope for each reviewer that is best. So an important point about this procedure is that each reviewer has a different intercept. They have a different average value that they gave to their two grants. They also have a different slope. So the slope that minimizes the sum of squared errors for reviewer number 41 is slightly different from the slope for reviewer number 42, which is different than reviewer 43, and so on. So what I've done here is I've taken the procedure that we use to analyze groups of people, big data sets, and I've applied it to smaller subsets of our data. So each reviewer forms their own subset of the data, and I've just done this for each reviewer, so 50 times. Again, for each reviewer, the intercept represents, just on average, what did they give grants, what score did they give grants. And the slope represents to what degree did that particular reviewer give a different score to their low quality grant versus their high quality grant. I can then take those intercepts and slopes and think about treating them as I would treat any other outcome using the general linear model. So, for example, the intercepts, I mentioned each reviewer has a different intercept, so the intercepts have some variability. Each reviewer is going to be a little bit more harsh or less harsh overall. And there's also probably an overall intercept that minimizes the sum of squared errors when you're considering each of the reviewer-specific intercepts. So there's going to be some value at the center that is minimizes the average distance from each of the reviewer-specific intercepts. I'm basically treating the intercepts as its own new outcome variable that I've created. I can think about doing the same thing with the slopes. So each of these is a particular reviewer slope. It's a difference between the score that reviewer gave the low quality grants versus the high quality grants. There's some variability in that difference. So some reviewers responded to this quality manipulation to a lesser or greater degree. And there's probably some slope that is best in the sense that it minimizes the sum of the squared errors from each reviewer's individual slope. So one way to think about what we're doing, this is the data set where we started from. So we have the situation where we have multiple rows for each reviewer. What I've done is I've taken the 50 subsets of data, so taken each of these chunks of 2 rows. And then I've summarized those 2 rows with some quantities that I calculated. So I've calculated intercepts, sort of treating that each of those chunks of 2 rows as their own mini data set. I've also calculated slopes. So again, considering each of these chunks of 2 rows as a little mini data set. So I've started from a data set that has 100 rows, 2 for each participant, and I've ended up with a data set that has only 50 rows, because each reviewer gives me only one intercept and only one slope. Any questions so far?
pause for a second.
Yeah.
So. Like,
Any other questions? So this is an important idea, and if something is confusing, please do say something. Of course, this is not the only time we're going to be reviewing this idea, but this does form a lot of the basis of what we're going to be doing in this data.
I'm just confused about having two participant IDs for separate scores. Why would you need that?
This is one way of representing these data. So in the data management section, we talked about tidying data sets and how sometimes the tidy version of the data set involves giving multiple IDs for each row because you measure each person twice. I could also represent this data set in a wide way where I'd have one row per participant, one column for that participant's score for the high quality grant, and one column for the low quality grant. So I use that function called spread. Spread would transform this data set from one with 100 rows to one with 50 rows. That's maybe a little bit more familiar.
Yeah, I'm just thinking more from like an intuitive approach, like you would measure at time 1 and then time 2. That's why you would have two separate participant IDs for the same participant.
Well,
It's not necessarily
every time each participant shows up, they get the same ID. We want our ID variable to be constant for records.
So just for example here, time 1 you asked them about low quality grants, and then at time 2 you asked them about high quality grants.
Yes.
Okay, gotcha. Makes
Well,
sense.
when they asked at the same time,
Yeah.
you just asked them two different things.
Yeah. I mean, there are different ways of designing this kind of study. You could counterbalance the times because you don't want to see a practice effect where people just get better at reviewing. I don't know. There are different ways of designing this study. Let's just say that everything is simultaneous somehow in this particular example. And yes, there are different ways of structuring this data set. We'll actually get to that idea on Wednesday. There are alternative ways of structuring this problem and thinking about it in different ways. Other questions? So this is kind of a messy way of representing all this information on one graph. So I showed you the intercepts and slopes, and I showed you like multiple panels, one for each reviewer. So what I've done here is I'm showing all the data points on one panel, and I just drew a slope for each reviewer and a very faint horizontal line representing each reviewer's intercepts. And one interesting thing that you might see in this graph is that it looks very similar to the graph where there was no, I had 100 reviewers instead of 50 reviewers. The only thing that's changed is that I have a bit of information that I didn't before. I know that there's a certain point here that has a link with one of the points over here. So it's the same data, I just know a bit more about the structure of the data set, where I have some reason to pair sections of data that I couldn't pair together before. Okay. So that gives you like maybe a conceptual in to the way this kind of problem is structured. The idea is that you have a data set where you have some reason to know or some reason to believe that certain rows of the data set are linked. You find some sort of procedure to extract one number from those multiple rows instead of the, say, 2 numbers or 3 numbers, 4 numbers. Once you've extracted each of those numbers, each of those single numbers from your chunks of the data set, you can then use the general linear model. Almost as usual. There are some slight twists that I won't get to today, but that I'll talk about later in the evening. But that's the conceptual understanding here. You're summarizing chunks of data sets with single numbers and analyzing those single numbers that you get. So, okay, this is how we analyze this kind of problem in R4. You use LM, you've got an outcome variable, a predictor variable, and a certain data set. This is one way of analyzing the same problem, but with linked data. So there are a couple things that are new with this model. The first and most obvious is that we're using a different function. So we've got a problem that the regular general linear model doesn't handle in the most ideal fashion. I'll talk about ways to make things work a little bit using the regular general linear model in one second. But for the time being, just we're using a new function called Elmer. This new function comes from a new package called LME4. And it shares a lot of the same syntax as the LM function. So you can see we still have a formula after the function call. And actually, this part of the formula is exactly the same as it was in LM. So we still have an outcome variable called M-score, overall impact score. We still have a predictor variable called quality Dike, which is called dichotomous in this case. So that part is the same. What's new in the formula is the second bit. So I mentioned how you can think about basically applying little mini regressions for each reviewer, for each subsection of the data, those sections that are linked. So in this section right here, you're telling Elmer, this is the variable that tells me which parts of the data set are linked. Any parts of the data set that share an ID number, just an ID, are linked together. This part of the formula tells Elmer, this is the little regression that I want you to fit for each of those subsections. Just like regular LM, it gives you an intercept by default. So there's an invisible intercept here. You can think about 1 means the intercept. There's a little 1 in this formula. But we're also getting a slope for each reviewer. So we're seeing how each reviewer responds to the following information. So that's the new part of the formula. You've got the section on the outside, and then you've also got a section on the inside that tells LME4, this is the little formula that I want you to fit for each subsection of the data, where the subsection is defined by participant. There's a particular name that I'm not going to explain right now, but it will come up again for this part of the formula. These are often called random effects. there's a reason for it. Sometimes they're called mixed effects. But what I want you to think about right now is that the random effects are where you're fitting this little regression for each subsection of the data, for each participant, or each business, or each school, whatever. I don't have this on the slide, but I'll add it. So it's an important bit of terminology. This part on the outside, they're often called fixed effects. And again, I'm not going to explain right now the reason for that, but I just want you to have that bit of terminology. It'll make a bit more sense as I get in, when I get more into the cuts of how this works. This right here is technically not required, but you often have to use it. That bit on the outside controls what's called the optimizer. It's not something that you'll have to think about very much for the time being, but when you get to more complicated mixed effects models, often you do have to fiddle with the optimizer. It's not going to make sense right now. For now, just know that you often have to use the optimizer, and I'll get into later what that's doing and what it means. Then you have the data set as usual. So the new stuff are, you have new function, you have these things called random effects that involves fitting little linear models for each subsection of data. And you have this thing called an optimizer that helps the function work. So I'm going to show you the output that you get side by side with the non-repeated measures version of the data set where we don't have these links, and the repeated measures version. And we'll see what's the same and what's different. So this is our regular LM output. We went through it earlier in this lecture. And here's what Elmer gives you. So one thing to notice right off the bat is that we've got some new stuff, some new numbers that we've never seen before. We've got these things called random effects, giving you that bit of terminology, so you might guess that this has to do with those little mini regressions. There's this thing right here that's talking about REML, which I'm not going to explain right now, but that has to do with the optimizer. And we've got these things called fixed effects. So right off the bat, you compare the intercept that you get from the fixed effects from Elmer. It's exactly the same intercept that you get from LM. You can think of this as telling you the grand mean, or more specifically, the mean of the viewer intercepts. So you got those 50 intercepts, one for each reviewer. This is basically the mean of those intercepts. One thing that's different about this line is that we don't get a p-value from Elmer, whereas we did from LM. There's a specific technical reason for this that I'm not going to get into right now, but will matter as we get to more complicated models. For the time being, just know that you have to use a separate function, the capital A ANOVA function, not little a ANOVA, but capital A ANOVA, which is from the car package. This function has come up once or twice in the past. The main thing that you need to know about it right now is that it gets you p-values. It also gives you F values, which work basically, well, very similar to F values that you've seen elsewhere in this course. Another thing to notice now that we have our P and F values is that this F right here is a little bit different from the F that we got when we assumed no links between the various rows. And the p-value is so small that it's not really apparent here, but the p-value would be different too because the f-value is different. Another thing that's a little bit harder to see here is that our degrees of freedom are different. So up there on the, after error df, you have 98 degrees of freedom. That's what we had on the data set with no links. Now we have 49. The reason this happened is that, again, you can think about applying these little miniature regressions, one for each reviewer, which gets you 50 scores, one for each reviewer. So what we're analyzing is those 50 reviewer intercepts instead of 98 individual values. So the reason our degrees of freedom have gone down is that we have 50 reviewers rather than 100. And we're deriving quantities from each of those individual reviewers. If we look at the next line, the slope for quality is has exactly the same value in the unlinked version of the data set where we have 100 reviewers and the linked version where we have 50 reviewers. So that's the same as we saw with the intercept. But if we look down here, our F value is different, and this time it's a little bit higher than it was before. And our p-value is different. We can actually see that on this for this particular comparison. So one thing that we've learned here is that, at least for this type of problem that we're working with this type of data set, our coefficients remain the same across different ways of analyzing the data set. But our test statistics are different. And in addition, the number of degrees of freedom, the number of observations that we are considered to have is also different. It's half. I'm going to talk a lot more about why this is the case. That's another thing I'll talk about on Wednesday. But for now, just notice that coefficients are the same, but test statistics are different. And there are a couple different reasons for why the test statistics are different. So let's get into the other part of the output that is totally new. We have these things called random effects, and Elmer is telling us some variance values and standard deviation values. So I mentioned how, basically what we're doing is we're doing these mini regressions, 50 of them, one per reviewer. And you can think about those, the intercepts and slopes that you get from each reviewer as forming the new data set with 50 rows. Well, this variance right here and the standard deviation are essentially how variable those intercepts are and the slopes are. How much do they vary from reviewer to reviewer? So to show those graphically, showed you these two graphs over here, where each reviewer's intercept, is slightly different. So that standard deviation or variance tells you the degree of spread across these reviewer intercepts. And the one for the slopes tells you the amount of spread or the degree of difference across the reviewer slopes. So by default, Elmer tells you something about the amount of variability that you have across those derived quantities, those derived intercepts and slopes. This is different from LM because in LM, we only had one source of variability from source where there's only one prediction error. There's only one way we could be wrong. But here it seems like we have multiple. We could be off by the intercept or the slope. So this is an idea that I'm going to come back to more often later on in this unit. For now, just know that in addition to having, residuals, just that one residual, well, now we have sort of a residual for the intercept and a residual for the slope. It's not exactly like that, but close enough for the time being. Okay, so even though this was like this went fast, these are like very different ideas. And they're going to be really important for this entire unit. One is this idea that there are certain ways of linking rows across data sets. They could be defined by participants, businesses, whatever unit you think might cause your prediction error for one row to be similar to the prediction error of another row. And one way of understanding how to deal with that problem is to reduce those 3 rows or those 2 rows or however many rows you have to one row by doing little mini regressions on those chunks of the data set. So you can think about fitting a little regression that has the relationship between quality and overall impact 50 times, and that giving you a bunch of intercepts and slopes, however many reviewers you have. The reason you need to go through this entire process is, again, this idea that if there's some meaningful way of linking rows across data sets, if you have a prediction error that's positive for one row, it's probably also going to be positive for another row. That's a violation of the assumption of independence, and it's one of those very serious violations that makes the general linear model wrong. Another big idea here is that each of those derived quantities that you get, so your individual participant intercepts or individual participant slopes, has its own amount of variability. And that variability makes a difference with how this new type of model, the linear mixed effects model, works. All that variability is, again, is the degree to which each individual reviewer, or whatever your units are, varies from reviewer to reviewer. And then the other big picture idea is that, at least with the case that we've considered so far, and with this is true of an important class of cases, the coefficients that you get are going to be the same, but your test statistics are going to be different. So on Wednesday, we'll talk a bit more about the guts of this new model, also alternative ways of understanding it, alternative ways of understanding what it's doing. Any questions? Okay, well, that's all I have for today. I'll see you all on Wednesday.